So, covalent bonds are another type of bond, apart from ionic bonding. And covalent bonds come along when atoms decide to share. So, obviously I showed you that group 1 and 2 and 6 and 7 aren't likely to share. They're likely to give electrons or take electrons. So these ones would give electrons and form a positive charge. These ones would take electrons and form a negative charge. Covalent bonds are the ones in between these. Usually they form between 3, 4, 5, maybe 6, maybe 2, but definitely not 1 and 7. So the groups are the columns, remember. So group 1 and 2 will be metals, and these two groups are non-metals. And obviously we know group 8 are noble gases or ideal gases. So covalent bonds form when atoms share electrons between themselves. So we call one covalent bond when 2 electrons are shared, or one pair of electron shares. So one pair shared equals one covalent bond. You can also get double bonds. That's when 2 pairs are shared. Okay, so for example, we have hydrogens. Hydrogens only share one because hydrogen only really has one. Hydrogen's a tiny atom, it doesn't really have anything else to share, and it only fills up the first shell. So remember, the shells are filled, the first shell is filled with 2, the second shell is filled with 8, and the third shell is filled with 8 as well. That's how many electrons are in each shell. So for hydrogen, it only needs to fill the first shell, so it needs 2. And when one pair or 2 electrons are shared, that's one covalent bond. It gets more complicated though when you come across carbon or oxygen in certain things. So carbon in ethene, for example, is like this. Now ethene is in crude gas. Okay, so this is like that because the carbon is sharing 2 pairs with the other carbon. Alright, so we have, let's call the circles the ones from this carbon and the crosses from this carbon. So we have 2 pairs, which means it's a double bond, which is drawn like this between the carbons. Oxygen is another thing, so if you have O2, it will also have a double bond. And that's drawn exactly the same way. You have the O in the middle. This is just showing the outer shell, okay? That's why there's only one shell around them. And there are 2 circles, which comes from that, and 2 crosses, which comes with that. Okay. So, they can form simple or giant structures. Okay, so giant structures are just like the ionic lattice, and actually they get confusing. So sometimes diamond can be used as a kind of example of an ionic lattice, but really it's not. It is an example of a giant lattice, but it's a giant covalent lattice. And graphite is also a giant covalent lattice. So giant ones, they're similar to the giant ionic lattice in that they have high melting points. So high melting point and high boiling points. Okay. And that's because they have really strong structures. They have structures that all of the atoms share electrons, and they form massive 3D structures just like the one we had before. Okay, and they can form kind of cube structures sometimes. So for diamonds they form kind of cube structures. For graphite it's slightly different though. They can also form these structures, where it's not exactly a cube, but all of one layer is connected, and then you have another layer underneath, but that layer is all interconnected inside itself, but between the 2 layers you have only weaker kind of slippery bonds. So for graphite it's like this. So you could push down on a pencil and the pencil will keep this part, and the paper might keep this part. Okay, and that's why pencils work like that. Because one layer of the pencil will stay on the paper, forming your writing, the other forms the layer of the pencil. Okay, so simple. They have strong intra, which means inside, molecular bonds, which means, for example, oxygen, O2. We know that there's a double bond between the oxygens, which is really strong, but between the different, so inside here you have the double bond, but between here you don't have a double bond, you have weak intermolecular bonds. The intermolecular bonds are what really determine the melting point and the boiling point. So for this, you have really strong intermolecular bonds because everything's connected. There isn't really an intermolecular bond because it's all connected into one huge lattice. Well, with these, you do have molecular bonds. They're weak, so you get low melting points and low boiling points. And why does this matter? Why do these matter more than the covalent ones? Because melting is when these things can float around more between each other. And boiling is when you still have O2, but they're free to fly anywhere. They have tons of energy, so they form gases. Okay, so giant covalent structures, I gave you examples. Diamond, really strong, doesn't slip apart at all. Graphite can be used in pencils because it slips apart, but it has really strong layers. So the strong layers don't slip apart, but between the layers does. And then there's also silicon dioxide, or silica, and that's what sand is made of. And it's a giant structure, and it's strong, just like diamond. So silica and diamond are really strong, giant covalent structures. Alright, so then we can look at the kind of sort of structures that these things form. Okay, so metals can form a totally different sort of thing. They're still giant, but they're formed in a slightly different way. The bonds connect the different metal atoms together, but you have free electrons in between. And the free electrons in between mean that metals can bend easily, because the electrons in between allow them to kind of slide over each other. So you'll see things drawn like this. And they actually call these the metal ions. Well, they're kind of metal ions, but they're all connected in this sea of electrons. Now the electrons move between these different metal positive ions. So we could for example think that that's Na+, and it's a whole load of Na+ connected together, and all these Na+ are kind of sharing this sea of electrons. Alright, so what does this sea of electron mean? Well, I said it allows it to slide over each other, because the pluses can just simply slide over the electrons. Okay, it also means that the electrons can move, which gives it a kind of conductivity. Okay, the electrons can move charge. Alright, and also we call them malleable. Metals are malleable because they can be bent and hit into shape without snapping. They're not brittle, they're the opposite of brittle, they don't snap, so they're malleable. Okay, so how can we tell what sort of thing we're looking at? If we have just a random chunk of metal or a chunk of material that we're not sure if it's metal, if it's covalent, or if it's ionic, or non-metal. Okay, so we can probably look at these things. So we can look at the melting point, we can look at the boiling point. If it's high, then it's a giant lattice probably. But is it an ionic one or a covalent one? That's the question. Is it ionic or covalent? Okay, so how about we also consider, is it metal? Alright. So metals, what could we check for that? We could check, is it conductive? Okay. Alright, it could be conductive. Is it malleable? Does it get smacked into place without breaking in half? That means it's malleable. Okay? Alright, and we could check individual properties. For example, is it graphite? Can we draw on paper with it? Does it have layers? Okay, so these are all things we can look at. Generally, you look at melting, whether if it's melted, does it conduct electricity? And if it does, then it means, well, what frees charges when it's melted? Only an ion does. Molten equals electricity. Non-molten, high boiling point and melting point. Alright? Well, the difference between that, conducting electricity, and a metal conducting electricity is that metals conduct electricity while they're solid, which is why we can use copper wires, because copper is a metal and we don't need to melt it and have melted liquid throughout our wires, which would get really messy.